Hi guys. I don't know if y'all remember me. My name is Kevin Harris. I was the one that came and observed your class a while ago. I'm sure Lana's kind of filled you in on the situation that I'll be recording some videos for y'all. Just covering a couple of sections out of this next chapter for chapter 5. The one I'm covering today is inverse functions. Before I get started, I just want to say I hope everyone's doing alright. I hope everyone's staying safe and that we're able to, hopefully everyone's just getting through this crazy time. If y'all ever have any questions for me, feel free to reach out. Just if you have anything for me, if you need help with any of the content, or if you have any questions UTA wise, anything like that, I'm more than willing to help. Lana has all my contact information, and so she'll be able to give you that as needed. But yeah, let's go ahead and get started. So we're gonna look at chapter 5, section 3, which has to do with inverse functions. So let's see what we got here. So our objectives for this particular section is verifying that one function is the inverse function of another function, determine whether a function has an inverse function, and then finding the derivative of an inverse function. So the first two objectives are basically things kind of like recall, if you will, with a couple of added things in there that have to do calculus base wise, and then that last section, the find derivative of an inverse function, is something that's new. So let's see what we got here. So yes, inverse functions. And just to kind of recall what an inverse function is, if we look at a certain example, we have f of x equals x plus 3. So where we have our domain, it's just the numbers 1, 2, 3, 4, and our range B is 4, 5, 6, 7, and we can also rewrite the function as sort of like a set notation, where we have the set of ordered pairs. So 1 goes to 4, add 1 to 3, you get 4. 2 goes to 5, 3 goes to 6, 4 goes to 7. And now, of course, writing it like this, it's easier to find the inverse function, because now all we have to do is flip the coordinates. So for the inverse function, we go from B to A, and so we have 4 goes to 1, 5 goes to 2, 6 goes to 3, 7 goes to 4. And as you can see, if you're just looking at the pairs, the inverse is simply just, instead of adding 3, we're going to be subtracting 3. There we go. Okay, now inverse functions. Now remember, from inverse functions, one of the key of being able to tell if a function is of its inverse is also the domain and the range. So it's also very important. So basically what this slide is saying is that, of course, we have the compositions. F of f inverse of x is equal to x, and likewise, if we reverse the composition, we should still get the same thing. And that the domain of f ends up being the range of f inverse, and the domain of f inverse ends up being the range of f. So essentially the domain and range flip as we go from f to f inverse. Okay. So now we have our technical definition. So we say a function g is the inverse function of the function f when f of g of x equals x for each x in the domain of g, and g of f of x equals x for each x in the domain of f. So of course the function g is denoted by f inverse. So we read it as f inverse. We don't want to read it as f to the negative 1 power, because that's something entirely different. So that's why we call it f inverse. Okay. So we just have a couple of remarks. So if g is the inverse function of f, then likewise, if we start off with g, we would say that f is the inverse function of g. So they kind of go hand in hand. They pretty much go hand in hand. As we said before, the domain of f inverse is equal to the range of f, and the range of f inverse is equal to the domain of f. So like I said, the domain and the range flip for the functions as we go from the original to its inverse. And a function does not always need to have an inverse function, but if it does, the inverse function is unique. So as you might remember, a function can only have an inverse if it's quote-unquote 1 to 1. Not all inverses, so not all functions, such as like if you think about f of x equals x squared does not have an inverse function. But if the function that we're given does have an inverse, that inverse function has to be unique. There can't be more than one. This is probably one of my favorite sides of the presentation, is you can think of f inverse as undoing what has been done by f. So in that earlier slide we had where we had x plus 3, if you notice when we went back and when we did the inverse, when we flipped the coordinates, if you subtracted each of those x coordinates by 3, you would get the answer. So that's kind of what happened in that first one. Let me get rid of this. Apologize. So f of x equals, so if we start off with something like general, like x plus c, where c is just some kind of constant, then we have that f inverse would just simply be equal to x minus c. And likewise, if we have f of x equals cx, where c is a constant, preferably non-zero, then we have its inverse would be x over c. Notice that if c was 0, this whole function would just be 0. 0 is one of those functions that doesn't have an inverse because it's a constant function. Constant functions don't have inverses because they're not one-to-one functions. So one way you can think about it is addition and subtraction are sort of inverse functions, inverse operations to each other, and the same can be said about division or multiplication. So for our first example, we just want to verify that these two functions are inverses of each other. So we have f of x equals 2x cubed minus 1, and g of x equals the cube root of x plus 1 over 2. Now the domains and the ranges of both f and g are all real numbers. So that's one thing you can that's already good. But this is also something when you're doing verifying inverses and whatnot, this is something you definitely want to check. This is very important. So if you start off, the way we verify is we have to show both of the compositions. So we can start off by looking at f of g of x, which remember when we're plugging in, notice what we're doing to x and f. The first thing we're doing to x is we're cubing it, then we're multiplying it by 2, then we're subtracting by 1. So likewise, we're going to take this whole thing, plug it in for x. We're going to cube it, which the cube gets rid of the root, and then we're going to multiply by 2. These 2's cancel out, and then we're going to subtract 1. So then we have x plus 1 minus 1, which gives us x, which is what we wanted. Likewise, we're going to do the same thing. We're going to turn it around, and we're going to say, so now for g, keep in mind for g, the first thing we do is add 1, divide by 2, then take the cube root, which is, like I said, if you sort of talk it out, you can realize that these are inverses of each other because the operations you're going backwards, but you're also doing the opposite operations. And so I'll get into that right after we finish this. So g of f of x equals the cube root, and then we plug in the 2x cubed minus 1 where the x was. So we're going to add 1 first. That gets these 1's cancel out. 2 over x cubed, 2x cubed over 2. The 2's cancel out. And then we have cube root of x cubed, which the root and the cube cancel out. So we're just left with x. So what I was mentioning a minute ago is, like I said, for f, when we're doing our operations on x, you can kind of write them out in steps. So step 1, we're cubing x. Step 2, we multiply by 2. Step 3, we subtract by 1. So then likewise, for its inverse, we're going to go backwards on those steps, but for each step, we're going to choose the inverse operation. So our last step was to subtract by 1. So now our first step is going to be to add 1. Our next step over here was to multiply by 2. So likewise, our next step over here is going to be to divide by 2. And then our first step was to cube it. So root it to the power 3. That was our first step. So now our last step is going to be the inverse function of the cube, which would be to cube root it. So whenever you're taking something to the nth power, its inverse operation is just, you're going to take it to the nth root. And likewise, if you're starting off with the nth root, then its inverse operation would be just to take it to the nth power. So a square goes with a square root, cube root goes with a cube root, a cube goes with a cube root, and then an nth power goes to the nth root. goes with the nth root. Okay. Now, if we look at the graphs, you have that. So we verified the compositions, both of the compositions equal x. So we know that they're inverses of each other. If you look at the graph, you can see that they look very similar and that there's kind of a weird reflection going on. And so when you draw the graph 2x cubed minus 1, that's this first one, that's this black one. And when you get the g of x, the cube root of x plus 1 over 2, you get this one, which is this slight red one. And notice that they're actually reflected across this y equals x line. So then we have a general statement. Just exactly what I said. We had the graphs of f and f inverse. They're mirror images of each other with respect to the line y equals x. And so the graph of f inverse is a reflection of the graph of f in the line y equals x. And so that should technically always happen. And we have the graph of f contains the point AB if and only if the graph of f inverse contains the point VA. Remember that very first example with the x plus 3, what we did when we found the inverse was we just switched the coordinates. That's essentially what happens on the graphs. That happens at every single point. The x and the y coordinates flip. And that's called the reflective property of inverse functions. And for the next part, we will talk about the existence of an inverse function.